Note that for even rather small len x, the total number of permutations of x is larger than the period of most random number generators. This implies that most permutations of a long sequence can never be generated. Sample population, k. Return a k-length list of unique elements chosen from a population sequence, used for random sampling without replacement. Returns a new list containing elements from the population while leaving the original population unchanged. The resulting list is in selection order so that all subslices will also be valid random samples. This allows raffle winners to be partitioned into grand prize and second place winners. Members of the population need not be hashable or unique. If the population contains repeats, then each occurrence is a possible selection in the sample. To choose a sample from a range of integers, use X range as an argument. This is especially fast and space efficient for sampling from a large population. The following functions generate specific real value distributions. Function parameters are named after the corresponding variables in the distributions equation as used in common mathematical practice. Most of the equations can be found in any statistic test. Random returns the next random floating point number in the range 0.0 to 1.0. Uniform a, b return a random real number n such that n is less than or equal to n and less than b. Beta variate alpha, beta. Beta distribution. Conditions on the parameters are alpha greater than -1 and beta greater than -1. Return values range between 0 and 1. Now let us focus on random numbers in Perl. Until fairly recently, CPUs had no direct way to generate random numbers. Intel's Pentium 3 introduced a hardware random number generator that uses thermal noise to generate high-quality random and non-deterministic numbers. But prior to that, systems that needed good random numbers had to rely on add-on borders or other external inputs. The problem is that the whole point of computer programming is predictability. Given the same input, a program will always follow the same path to completion. That makes it impossible to generate random numbers with an algorithm. For all we know, it may be impossible, period. While thermal noise from a semiconductor certainly seems random to us, if we really understood the physics, it might not be at all. If string theory is real, then the arrangement and orientation of these strings might affect their vibration, which in turn affects the behavior of electrons, and etc. It is quite possible that the universe is deterministic. We really are not in any position to even guess right now. The real question is, does it matter? And the answer is both yes it does and no it doesn't, depending on why you asked. On the other hand, we have apparently non-deterministic events like how many visitors this website will have today. That's an apparently very random number determined by perhaps hundreds of conflicting factors such as news events, advent of security challenges, the weather, Google ranking, well beyond any ability to calculate. Yet, it's pretty easy for me to guess with a few hundred what that number will be, because in large enough populations the random behavior of individuals is unimportant. Statistics and other indicators can tell us what the general group behavior will be. From this point of view, it doesn't matter if individuals are not deterministic, because group behavior is not. The same thing is true of systems like our own Earth's weather. The problem with computer generated random number is they may not be very random at all. Almost all computer languages have some method of selecting a random number, but in fact it's not really random. The following Perl script will generate the same results every time it is run. If you saw that run once, you'd think it was giving you random numbers. Run it again and you get the same 10 numbers. The numbers will not change no matter how many times you run it. So obviously they aren't random at all. That's because it is really only pseudo-random. The argument given to SRAM seed, the random number generator, and it will always generate the same numbers in the same order for the same starting seed. However, if we seed SRAM with something more random, we get better result. So, how do you get more random? Linux and other operating systems may provide a /div/random and /div/unrandom. Don't assume you know how these work. Mac OS X and Linux both have these, but the man pages are quite different. Perl has a truly random module that uses interrupt timing discrepancies to get random numbers. But do we know that the discrepancies are truly non-deterministic? Like the thermal activity of a semiconductor, it might actually be predictable. With sufficient knowledge and computing power, any of these things might be as trivial as our random second implementation. Many systems have the PRNG library. Many versions of SSH use that. If you ever generate a GPG key, you probably remember this. Think a situation you want to make random numbers in a given range inclusive, such as when you randomly pick an array index, simulate rolling a die in a game of chance, or generate a random password. The solution is use Perl's rand function. This code generates and prints a random integer between 25 and 75 inclusive. The rand function returns a fractional number from 0 up to its argument. We give it an argument of 51 to get a number that can be 0 or more, but never 51 or more. We take the integer portion of this to get a number from 0 to 50 inclusive. 0.99999 will be returned to 50 by int. We then add 25 to it to get a number from 25 to 75 inclusive. A common application of this is the random selection of an element from an array and generating a random password from a sequence of characters. Scheme. Random number generating random.plt library is available through plant. Examples: